Actually, it'll be very useful for this class to have the table of charges that we had last class written down. So I'm going to ask for your help in doing that. So let's say that we have on this side we had the various charges. So let's say that we had SU n and U1. Say these guys came from the left, meaning acting on Q's. You guys remember what we were talking about, right? We were talking about n equals 1 QCD, n equals 1 Yang-Mills theory, with NF quarks, which we call Q's, and NF other quarks, which we call Q tildes. Okay, and the Q's were in the fundamental, the Q tildes were in the anti-fundamental. Both of them were chiral superfields. The scalar part of Q we sometimes call Q itself, and then correspondingly there is a fermionic part of Q which we call lambda. We have in addition the gauge field. The gauge field has the gauge boson and it has the gaugino. We call the scalar the fermionic part psi. And there's a gauge field and the gaugino we call lambda. These were the SU NF and the U1 charges associated with Q. Then we had the SU NF and U1 charges associated with Q tilde. And then finally there was this U1, let's call it R prime charge, the baryon, the R symmetry that's going to turn out to be anomalous. And in addition, then you remember that the difference between these two U1s was non-anomalous. The sum of the U1s was anomalous. And then some linear combination of the sum of these two U1s and this quantity and this quantity was a non-anomalous R charge. And so people please help me fill up this table. We'll need parts of it in what we're going to be doing, so help me. So of course this was in the fundamental and had charge 1. This was 0, whatever, identity. If I write 0, it means identity, okay? Is that okay? 0 and 0. Okay? And under R symmetry, Q itself, under the naive R symmetry, Q carried no R symmetry charge. Remember what the naive R symmetry charge was? The naive R symmetry charge was 1 under which the gaugino carried charge 1. Okay, so it was an R symmetry charge under which W was charged with charge 1, and theta was charged with, what is it, 1 or minus 1? Let's see, because d2 theta is like 2 derivatives of theta, so it's also charge 1, because we have to, 2 derivatives of theta and W squared together has to be, right? So this naive R symmetry had W had charge 1, theta had charge 1. Okay, and therefore psi carried charge minus 1 because Q was uncharged, but Q had an expansion term which is theta psi, so psi carried charge minus 1. So let's get these charges down. Okay, so this guy had charge 0, but let's fill up fundamental 1, 0, 0, minus 1. And here this was 0, 0, fundamental 1, 0, and this was 0, 0, fundamental 1, minus 1. Lambda, you remember, carried charge 1 under the naive R symmetry, so that was easy, and all these guys carry none of this flavor charge. Okay, V mu is uncharged under everything. Okay, and then we defined this U1R to be equal to U1R prime. So let's say the relationship of the charges. So Q is nothing to do with supersymmetry, it's charge. Okay, I hope that won't confuse. QR is equal to Q R prime, and then we got some numbers, n minus nf. Somebody help me with that. Times, let's say QU1 plus QU1 tilde. Yes. 2 into n minus nf by 2nf. Okay, so these 2's cancel. And this is multiplying, Diksha, sum of these two U1s?
With the minus sign.
With the minus sign.
Oh, okay. No minus sign.
No minus sign, plus. Okay. So R is the true symmetry. R is the true symmetry, and this is correct, right? R prime is the true symmetry, then let me change it here. Thank you. And now this is correct. So then I'll write R prime in terms of R and with a minus. Okay, excellent. And then using this, let's see, so I'll check that we've got this correct by seeing if we fill out the table right, and I can get it right. So this guy had charge 1 under this, so it's 1 minus this. Sorry, it's 0 minus this, so this is just minus n minus nf by nf. Okay, and similarly for this, minus n minus nf. Please tell me if I'm getting something wrong. Okay, whereas this guy carried charge minus 1 under QR, okay, and also carried charge 1 here. So we have minus 1 minus n minus nf by nf, which is equal to n minus nf by nf, which is equal to minus nf minus n minus nf. Minus n by nf, but what am I doing wrong here?
No, but there's no wrong. There's nothing.
It was correct? Ah, thank you, plus, thank you. Minus n divided by nf. Thank you. Minus n divided by nf and minus n divided by nf. And lambda carried charge 1 and still carries charge 1 because it doesn't mix with the U1s, and this still carries charge 0. Okay, so we've got this nice table of charges under all our symmetries. Okay, and at the end of the last class, we had obtained this Affleck-Dine-Seiberg superpotential, which went this way. The W was some number, so I'm leaving out the number. It's times lambda to the power lambda by det m to the power, help me here, was it 3 n minus 3 nf? Oh, n minus nf? N minus nf. N minus nf. Is this correct?
Yes.
1 over n minus n. Yeah, thank you. 1 over n minus n. And lambda to the power?
3n minus.
3n minus nf. Exactly, thank you. 3n minus nf. Excellent. Excellent, excellent. So we obtained this Affleck-Dine-Seiberg superpotential, right, of course, which was of this form. Okay, and one last bit of reminder. Okay, one last bit of reminder goes as follows. We had the beta function, of the Yang-Mills theory involved a coefficient, right? So dg squared by d log lambda, okay, has a coefficient which, in the case of supersymmetric Yang-Mills theory, so as lambda there's a minus, and in the case of supersymmetric Yang-Mills theory, is proportional to n minus 3nf, okay, times g squared squared, okay, and in the I'd written this with a g, but it's actually with a g square, okay. So, and at the end of the last lecture, we integrated this. There are also some 8 pi's which I have not written here. We integrated this, and we got the equation e to the power minus 8 pi square, I think, or 8 pi by g square, okay, is equal to lambda by lambda naught. Let me check this. So this at scale lambda by lambda naught to the power 3 n minus 3nf. Let me check if I've got the thing correct. If I take lambda to infinity, this side goes to infinity, but it should be minus infinity. So lambda naught by lambda. Now if I take lambda to infinity, this side goes to 0, and since g goes to 0, that's correct. Yeah. Okay. So the running coupling constant in n equals n equals 1 supersymmetric Yang-Mills theory, just by computing the one loop beta function, is given by this formula. As we explained last time, the fact that in the case n minus nf is equal to 1, you can think of this, you can derive this independently by coming out of an instanton calculation, okay, is explained by this fact, because you see this lambda here is the same as this lambda naught, right? It's the fixed scale in the problem, not some running scale, okay, and that is the same as e to the power minus 8 pi by g squared, which is also what an instanton action is proportional to. Okay, fine. So this was a reminder of everything we discussed in the last class. Any questions or comments before we proceed? Okay, great. So you see, we have the superpotential, and one last thing to say is that we are always working in the case nf here is less than n. We'll turn to the cases with n greater than or equal to n, nf greater than or equal to n in a bit.
Is it 3nf less than n?
No, we've been working in the case nf less than n. So there are two different places. First place that's of interest is nf is equal to 3nf is equal, 3nf is nf is equal to 3n. Have I got this right? It's 3n minus nf. Sorry, this was 3n minus nf, and this should have been the same. Yeah, 3n minus. That's what your question was? Yeah, thank you. It would not work. Yeah. It's 3n minus nf. Thank you. It should be the same 3n minus nf here that appears here. Right? That's why it's a one instant thing. 3n minus n. Okay. Notice, by the way, that this tells us, this beta function tells us that the range of theories where this supersymmetric Yang-Mills theory is well defined is nf less than, or perhaps less than or equal to 3n. Okay? Because when nf is greater than 3n, this theory has a coupling constant that grows in the IR. And then whether it's well defined or not in the IR is a matter of whether there exists some fixed point from which the theory can flow. Okay? The way we usually define QCD-like theories is have them free in the IR and let them flow. Sorry, UV. When I said IR, it's always UV. We usually define QCD-like theories to having them free in the UV and have them flow to something non-interacting. That only works for NF being less than 3n. We'll come to the case NF equals 3n in a bit. But in the other case, the theory may be well defined. There may be a way of giving meaning to this theory. But the way we will give meaning to this theory is having it defined as a flow starting from some UV fixed point, which we will have to define. Okay, so just writing down some Lagrangian like this doesn't give a definition to that theory. So that's a different level. Just this Lagrangian defines a theory all the way to the UV, only for the case of NF less than 3n. This is clear, right? This is well defined in the Lagrangian because it means in the UV it's free. Then we know the theory in the UV, and then it flows to wherever it flows to. Okay, so we've got a well-posed question to ask. What is the IR dynamics of this theory, which is free only for NF less than 3n? We've been looking at one third of that range, which is NF less than n. So there's more to explore. Okay, excellent. And we will start exploring some of that more today. But excellent. Okay. Now, right at the end of last class, we started talking about the vacuum structure of this theorem. Okay? So, there's what we get, of course, from the superpotential. But more importantly than that is what we got from just the classical potential, namely the D terms. Okay? So, you remember that our D terms were of the form Q, T, A. So this is Qi, Ta, Qi dagger or star. Okay, maybe we will write it this way: star with a dagger with this here, minus Q, so plus Qi, and then this is sum over I, or I runs over all the flavors. I is equal to 1 to NF. Okay, plus some Q tilde Ta of so this is the fundamental, this is Ta of anti-fundamental. Okay, so Ta Qi tilde star. This was dA. Okay, and then our full potential in the classical theory was sum over A dA square. Okay. Now there are two or three things we can ask about this. The first thing is that this potential came from the classical Lagrangian. It came from W alpha W alpha. So W alpha W alpha is just a classical Lagrangian, and like the superpotential got renormalized in the quantum theory, could be that we get some renormalization of this W alpha W alpha term. It could be that we will have some coefficient behind the W alpha term built out of Q's and Q tildes in the actual quantum theory. Okay? But if you remember, and so the actual potential here, this classical potential, could well be renormalized in the quantum theory. But if you remember, the way this potential got renormalized was by taking the flat metric. Okay? By taking the flat metric and replacing it by some metric involving some functions of phi. Okay? The net thing that I want to say is this, that even though the actual form of the potential can get renormalized, it will always be a quadratic form in dAs. That you can just see from very general grounds. Okay? And therefore, the condition that dA is equal to 0 always gives you the space of zeros of this potential. Independent of the details of what kinetic term, what function of phi's could appear behind these dA kinetic, behind the W alpha kinetic terms. Okay? This one can argue very generally just by doing the. We looked at, and I haven't presented the algebra of this for you in class, but we presented the algebra for something similar. The similar thing was that the kinetic term of the scalar fields, when you multiplied it with some function of the scalar fields, became constructed like a sigma model out of a metric that was not the flat metric, but instead was a metric built out of those scalar fields, right? So just like in that case, if you want that term to vanish, doesn't matter what the metric is. If d mu phi is 0, that term will vanish. Something sort of similar happens here. Okay? And so dA equals 0 will be the space of minima of this part, the d term potential, quite independent of details. Okay? Now what we're going to use this classical potential for is not anything detailed, but only for computing the space of classical, the minima of this classical potential. Okay? So we're going to study the solutions to the equations, this dA is equal to 0, where dA is given by this. Okay. So is this clear? The question that we're going to ask ourselves is, of these 2NF complex scalar fields, 2NF times n complex scalar fields, what can we say about what values of these 2NF times n complex scalar fields will set dA equals 0 for all A? Okay? This will be the space of zero energy configurations from D terms, may or may not be zero energy from the point of view of F terms. Okay, question clear? Okay, we're going to try to characterize the set of fields that have dA equals 0 for all A. Okay, now the first thing that we need to do is to understand what the relationship is between this TA anti-fundamental and TA fundamental. Okay, so perhaps the simplest way of saying it is TA anti-fundamental. You know, we're writing U is equal to e to the power IT. Okay, so TA anti-fundamental is minus with a complex conjugate. TA fundamental. But since these guys are all Hermitian objects, complex conjugate and transpose are the same thing. Okay, so let's write this as minus with transpose. Okay, great. So now I want a configuration in which these guys vanish. Okay, one way to get this whole thing to vanish is for things to vanish pairwise. So if what comes from I from Q kills what comes from I from, let's say, I equals 1 from Q, kills what comes from I equals 1 for Q tilde, and then same for 2 and 3 and so on, then everything will be good. Okay? So, now, this guy has this transpose. Okay? This guy has this transpose. So, if we manage to make QI's, so now see, suppose we have, for the ith guy, we have more than one color turned on. Let's say for the first guy. Okay? We have more than one color turned on. Then we're going to get contributions from off diagonal terms as well. Because suppose we have color 1 and color 2 turned on, then there will be a 1-2 term. On the other hand, if for the ith guy, let's say it's first flavor, only the first color, for instance, is turned on, then this T matrix will be completely diagonal. Okay? If the T matrix is completely diagonal, the fact that there's a transpose there doesn't matter. And then there is a very easy way of solving these equations. Just turn on only one color for each flavor and make Q equals Q tilde. then you see that these DAs all vanish. Okay? Now we're in the case where there are more colors than flavors, because NF is less than N. Okay? So we turn on the first color for the first flavor, the second color for the second flavor, third color for the third flavor, and so on. This will do the job. Okay? So one configuration that obeys this, that sets all DAs to 0. Okay? So one configuration is this. So let me write Q as a matrix, and I'll write it as a matrix where this is flavor and this is color. Okay, and I write A1, A2 up to ANF. Okay, first flavor has only the first color turned on. Second flavor has only the second color turned on, and so on. And then also write Q tilde, okay, is equal to Q tilde is equal to A1, A2 up to ANF. By sort of construction, those terms cancel flavor by flavor in this case. Is this clear? Okay, and therefore we've got at least one set of configurations labeled by NF complex parameters.
Shouldn't this be star of A1
No, because you see,
it's a
transpose. We've taken care of that star. Yeah, we don't want to do anything anti-holomorphic. We've taken care of that by remembering that in this group, in this representation space, star is transpose. The fields themselves are just going to be what they are. Okay? All good? So this is one set of configurations that solves this deflatness condition. Now something you can try to check is the following. Every configuration that solves this deflatness condition is of course not this. For instance, we needn't have turned on the first color with the first flavor, we could have turned on the second color with the second flavor. Okay? Or more generally, of course, once I've got configurations like this, if I act on this configuration with any global symmetry, or I act on it with a gauge transformation, since this thing is symmetry as well as gauge invariant, this dA thing will continue to be 0. Okay? But one thing you can check, and I leave that for you as an exercise, is that the most general solution is global symmetry or gauge transformation of this configuration. Okay, so up to global symmetries and gauge transformations. Okay, so up to global symmetries and gauge transformations, this is the most general solution to the deflatness conditions. Okay, so you see the situation that we had here. In the absence of the superpotential, go on.
For the gauge symmetry, we'll have to apply U on Qn, similarly U dagger.
U dagger and Qn dagger, yes. They have to transform like they do under their gauge transformations. But you know, nothing physical like the fact that the energy is 0 in this configuration can depend on that transformation. Right? So, the most general configuration is this times a global symmetry transformation and a gauge symmetry transformation. In fact, you can act on it with any of the global symmetries there because it's just a question of, you know, classical action. But the R symmetries don't act on Q and Q tilde anyway, so it's really the UNF times UNF. Okay? Great. Now, all the dynamical information that we can get with looking on the space of vacua, we can get by looking at these particular configurations, because we got something related by, let's say, global symmetry. Physics is not going to change. Okay, so we will work with this class of configurations when we want to discuss things like vacuum stability. Okay, on this class of configurations, let us compute this meson operator. Mij, which is equal to Qi Qj tilde. Okay, it's clear what this is. This is equal to on this special class of configurations, this is delta Ij times Ai square. Right? Something else that is that we used a lot was det m. Okay, and that is equal to product over I, Ai squared, I is equal to 1 to Nf. All good? Okay, excellent. So, what was the situation? In the absence of this superpotential here, okay, we had this moduli space of vacuum. The moduli space of vacuum are labeled by these 2NF complex parameters plus global symmetries. Okay, so a large number of different vacua. Now the question is, what does this superpotential do to the space of vacua? Okay, and we will see this in formula in 2 minutes when we start looking at the theories with masses. But it's very clear visually from the shape of the potential that it will drive all of these. That there will be no solution to the superpotential flatness conditions. That the energy will be zero only at all a's equals infinity. Right? You can see that sort of very clearly if we plug this in here. So this becomes product of these a's. Okay, raised to some positive 1 over raised to some positive power, and then the potential obtained by varying with respect to each of these a's will be derivative, then mod square. You see it's sloping down, right? Is this clear? So, so even when we impose the deflatness conditions, the theory with the superpotential here has no vacuum. Okay? Now we want to discuss what happens, how to salvage this. Okay? So what we're going to try to do is to introduce a mass. Okay. But actually, one little thing before that. So in 2 minutes we're going to introduce a mass into the problem. But one little thing before that. Before this, there's one little consistency check of the superpotential that one can perform, which sort of goes as follows. Suppose we are on this space of vacua, okay? Suppose we're on the space of vacua and we take AN, let's say ANF, and make that much greater than lambda. Okay? So now what's happened? You see, what we've got is this one quark, namely the nth quark. Okay? We've got this one quark, namely the nth quark, okay, has an expectation value which is much greater than the strong coupling scale of our n equals 1 QCD. Now remember that the running of the gauge coupling, okay, that the running of the gauge coupling happens according to the beta function of QCD. But you know, if you've got this first quark with this expectation value turned off at this very high scale, the running will happen according to the beta function of this this QCD theory up to that scale. After that scale, for below that scale, this theory is going to see the fact that it's Higgsed. Right? Because you see, this A and F here was an expectation value of a colored field. At scales below A and F, the SUN gauge theory is effectively Higgsed down to SUN minus 1. Is this clear? So you see that the effective beta function running at scales below A and F is going to be governed by a different beta function. One associated not with the beta function of SUN theory, but SUN minus 1 theory. Is this clear? Okay? So now let's see how this works sort of quantitatively. Okay. Moreover, yeah, okay, let's see how this works quantitatively. Okay, so see, the beta function here, this beta function equation here tells us how the running of the gauge coupling goes as a function of scale. So this thing here, so now what we're going to do is to take the scale of this theory, this coupling constant of this theory, and follow how it runs as a function of scale. So there are going to be two separate runnings, one for lambda greater than lambda than ANF. In this case, the coupling constant is going to run just like this. E to the power minus 8 pi by g squared lambda is equal to lambda naught by lambda, okay, to the power 3n minus nf. Right? Now, for lambda less than ANF, okay, for lambda less than ANF, sorry, just 1 second. Okay, for lambda less than okay, so for lambda less than ANF, we're going to have e to the power minus 8 pi by g squared lambda being equal to some lambda tilde by lambda, and now to the power what? Good. So first we get 3 into n minus 1 minus NF is also decreased by 1 because the Higgs mechanism eats up this last gauge, this quark. Okay, so we have NF minus 1.
So it will eat up both Q and Q tilde.
It will eat up both Q and Q tilde. So effectively,
Decrease by 2 the number.
no, but the number of flavors is counted only as how many Qs and separately how many Q tildes. Right? Yeah, so it's with this convention that there's NF Qs and NF Q tildes that the beta function is 3n minus NF. Yeah. Okay, excellent. So, as Diksha said, both the Qs and Q tildes get eaten up by the Higgs mechanism, and we have this running. But these two things have to be equal at lambda equals ANF. Okay? And so if we set lambda equals ANF, we get lambda naught tilde by A nf to the power 3n minus nf is equal, 3n minus nf minus 2, right? Minus 2. Minus 2 is equal to lambda naught by anf to the power 3n minus nf. Is this clear? Okay? And therefore, we get lambda naught tilde. We get the formula lambda naught tilde to the power 3n minus nf minus 2 is equal to, this has higher, so lambda naught to the power 3n minus nf divided by anf square. Did I do that right, please? Let's check dimensionally. The total power of dimension here is 3n minus nf minus 2, and that's also there. So that's okay. Okay, so we have that the prediction just from starting from this theory with n colors and nf quarks, and using simple general expectations of physics, we expect that the low energy theory is that with n minus 1 colors, nf minus 1 flavors, and an effective lambda naught tilde given by this quantity here. Okay, but this is enough for us to predict what the superpotential is of the theory with colors n minus 1 and number of flavors nf minus 1, because we just plug. We know that the superpotential of the UV theory is lambda naught to the power n minus 3nf. 3n minus, I keep making 3n minus nf, thank you. What? N minus, yeah, 3n minus nf. 3n minus nf. 3n minus nf divided by det m to the power 1 over n minus nf. But this det m is just an squared times det m tilde. Okay, so this is equal to lambda naught 3n minus nf times an squared, anf squared, whatever we call it, anf, times det m tilde to the power 1 over n minus nf. Okay, but this we just saw was equal to lambda naught tilde to the power 3 into n minus 1 minus nf minus 1 by det m tilde the whole to the power 1 over n minus 1 minus nf minus 1. Where I've used the fact that n minus 1 minus nf minus 1 is the same as n minus nf. And this is exactly the superpotential that we independently expected for the theory with n minus 1 colors and nf minus 1 flavors. Okay, you see how beautifully it's working? You see how beautifully it's working. Now, of course, you might say, look, of course, you might say, well, this relationship is very crude. Maybe it appears with the number 5 here. Okay, so then this relationship here will have a number 5. Anyway, we were working up to constants. Okay, so that number goes away if we're working in terms of up to constants. Now there is this claim, which I'm not sure how clear it is, that there is a regulation scheme, there exists a regulation scheme, in which that relationship is exact with number equals 1. Okay? Seiberg makes that claim, maybe it's true, maybe, I don't know, but it sounds like anyway, it doesn't matter. Up to constants it works. Okay? Maybe there's some regulation scheme that works even better, even including constants, but at least up to constants it works. Okay? These numbers are always regulation dependent. So, in what does lambda not mean? That depends on your regulation scheme. And none of these things are very, very universal, at least up to constants it works. Okay? So that's great. Fine. Okay. Now, this check we did even in the theory without masses. Now we're going to try to understand what happens to this theory when we add masses, and we'll be able to do further checks like this. Okay. Okay. So, the next thing we're going to try to do is to take our UV theory and add to it, take our UV theory and add to it superpotential, which is equal to MNF QNF tilde. MNF is a number, and QNF tilde are our superpotential, our chiral multiplets. Of course, the gauge indices are contracted in the way that is possible because N transforms in the fundamental, as Q transforms in the fundamental, and Q tilde transforms in the anti-fundamental. Okay? So this is the thing we're going to do. And once again, we're going to ask the question, what happens to the deep UV theory, deep IR theory? What happens to the deep IR theory? What is the effective superpotential that governs the dynamics of the deep IR theory? Okay. So we go sort of back to the drawing board. We've already seen that one superpotential okay. The way we're going to function is this. We're going to pretend that MNF is the expectation value of a chiral superfield. Some very massive chiral superfield that has some very strong potential, so it's fixed at constant. It has very high mass, very strong potential, so it's fixed at constant. Okay? We're going to pretend that so that we can conclude that whatever the modification is, it's going to preserve all symmetries provided we have first, it's going to be holomorphic in MNF. That's the first really important thing. And secondly, it will preserve all symmetries of the theory provided we also transform MNF in the appropriate way so that under the transformation the original superpotential preserved all symmetries. Okay, so let's look, for instance, at the R symmetry. Okay, so first we've got okay, let's look, for instance, at the R symmetry, the R prime symmetry. Okay, under this R prime symmetry, Q times Q tilde this thing has to transform like dimension, like R symmetry 2 in order to be to respect that symmetry. We can make it do that if we give a certain R symmetry charge to this MNF. And now we're going to calculate what that R symmetry charge is. Okay, so we want R of MNF, R prime of MNF, okay, plus now whatever this R charge is here for Q and Q tilde.
MNF
Yes. So I'm imagining, MNF is of course a number, but I'm imagining that there is some bigger theory in which MNF is a field, and in that big theory there is some vacuum, which is some very stiff vacuum, so that M cannot fluctuate. It's got very high mass in a very stiff potential, which sets it to be a particular value, MNF. So there's some very strong superpotential. Okay, the only reason I do this is that it helps me easily generate ward identities that I could calculate anyway, but it helps do it fast. See, because if it was a field and it was a field of the correct R charge, so that this R symmetry was preserved, okay, then that would have to be a symmetry, then the R symmetry would be a symmetry of the final IR theory. Okay? Of course, when we include the R symmetry charges of M itself also. Okay? The advantage of thinking this way is twofold. First, it will give you all the ward identities of broken symmetry that would come anyway if you worked with M being a constant. But secondly, it makes it clear that this M can only appear holomorphically. Right? Because you cannot distinguish between this being an expectation value of some field, okay, and some number. But when you think of it as an expectation value of a field, that field has to be a chiral multiplet, because it's entering a superpotential. And only chiral multiplets can enter a superpotential. Okay? So if the appearance of this field, like the appearance of all others, has to be holomorphic. So the answer cannot involve an M star. Okay? This of course you can argue from other ways, basically from ward identities of supersymmetry. But this is the simplest way to say it. Is this clear, Diksha? Okay? Okay? So this R prime symmetry of this MNF field plus the R symmetry of Q and Q tilde, which is minus 2 into N minus NF divided by NF has to be equal to 2. Yes.
Quantum action should have the R prime symmetry.
What?
Quantum action should have R prime.
Yes. So, but the quantum action has the R prime symmetry only if the classical action had the R prime symmetry.
No, the classical action had R symmetry.
Well, the classical action also had R prime symmetry. Classical action had one larger symmetry than the quantum action. It was symmetric under 3 ones rather than 2. Okay? I'm going to only worry about those that are also preserved by the quantum theory, because the one that is preserved classically but not quantum mechanically is no use, because it will not be preserved by the quantum superpotential. Okay, that's why I'm only worrying about R prime. This is the same. Clear, right? Okay? So, if we assign M this charge under this R prime, if we assign it this charge, then R prime was preserved by our UV theory and therefore should be preserved in the IR theory. Is this clear? Okay, so we get that R prime of MNF is equal to 2 into, what is it? NF is going to be, is it N by NF? Can you check this, please? Yeah, looks right to me. Yeah. So R prime of MNF is equal to 2. So if we think of this MNF as a field with R prime symmetry 2n by NF. Okay? If we think of it that way, then we are allowed to preserve the R prime symmetry over there. Is this clear? Now you see, we have to preserve the SU NF minus 1 symmetry as well. We have to preserve the SU NF minus 1 symmetry because that's clearly preserved by the symmetry, by this action. I have to preserve the SU NF minus 1 symmetry as well as the SU NF minus 1 tilde symmetry. Okay? And so, basically, our theory can depend on what? It can depend on the Q's that are not NF, but only in the combination determinant of those Q's. Same argument as last lecture. Anything that preserves SUN from the left and SUN from the right, only way to make that is a determinant. Is this clear? So it can depend on the Q's that are not NF in this determinant fashion, and it can depend separately now on QNF because the SUNF has been broken down to SUNF minus 1. Okay? So another way of saying it is that it can depend on the combination determinant of the whole thing or QNF tilde. This clear? Okay? Fine.
MNF will be transforming under bifundamental, right?
Under if we want to preserve the SUNF, I'm not thinking that way. I'm only going to preserve the U1 R symmetry, R prime symmetry. I'm breaking the SUNF down to SUNF minus 1. You know, if I wanted to think of it that way, I should turn on general MIJ. Okay, that's why I don't want to think of it this way. Okay? Later in the lecture, we might think that way. It's all equivalent. Right? But I'm just willing to break SUNF down to SUNF minus 1. Okay? But I want to preserve the R prime symmetry. Okay? Now look. So what have we finally concluded? Our final superpotential must be a function of QNF tilde and the determinant, and it has to carry R prime 2 with this assignment of charge to M. Okay? Now I'm going to write down the most general answer for that. First, it can be lambda by det M to the power, what is this? I keep getting this confused. N minus 3n, no, 3n minus nf. About 1 over. Okay? So I've got this overall outside times a function of something. Now this thing, whatever it is, now should carry R prime charge 0 because the R prime charge is already saturated in this. Okay? But this guy carries R prime charge 2 and this whole combination carries R prime charge 2. Okay? And therefore MNF Q tilde Q divided by this thing this is R prime charge in neutral. We didn't even need the computation of what the R prime charge of M was, because whatever it was, this combination will carry 2 by definition. I just worked it out just so that you feel secure that it has a particular R prime. It didn't matter. Okay? And so we've concluded by symmetries, from symmetries, that the most general superpotential will take this form for some function of f.
This is taken the U.
No, I. That depends on what vacuum we have. You see, adding a mass does not necessarily break some symmetry. Right? Separate this discussion from the discussion we had 10 minutes ago. In that discussion we had no mass and then we looked at a vacuum which broke symmetry. Here also we may be forced to look at vacua that will break symmetry, but that will happen dynamically. This is the superpotential of the theory, and then whatever comes out of it comes out. Is this clear? So it's some function of this. Now we want to know what we can say about this function. Okay. Now this is the argument that these guys give. The argument goes as follows. Let us suppose that we were working with M and F small. We'll soon see small compared to what? Okay, but we're in some configuration. One of these vacua of, let's say, A1 or A2. Okay, when all the A's in the theory are very large. Okay, if all the A's in the theory are very large, okay, then the gauge symmetry is weakly coupled, because you see all of the gauge running stops if we have SUN broken down to SU0, all gauge running stops at the scale of these A's. Okay, because we're also taking M to be very small, we'll see this self-consistently as we proceed. For now, just imagine that we're in some vacuum with all A's being very large. Okay, because all A's are very large, the gauge theory is very weakly coupled. Okay, so in the limit that all A's are taken to infinity, there should be no coupling effects in the theory. Okay, and in that limit then, the superpotential should just reduce. The fact that there was this extra mass term should make no difference at all, except that it's added this extra mass. There should be no quantum corrections to adding this extra mass term. Okay, so claim is that by looking at this limit A is going large. Okay, A is going large, and M and F being small. We'll come back to seeing why this is important in 2 minutes. Okay, we argue that this function here, let's call this guy T. This function must just become 1 plus T. Because in this limit then, the only effect of adding the mass is adding the mass term to the superpotential, and there are no further quantum corrections to anything else. I know this is a slightly slippery argument, okay. I know this is a slightly slippery argument, but I think it's correct. Okay, now the point here is that this function was an analytic function of its variable. So if you can get the form of this function by looking at any limit, you've got the function. Okay, so the claim therefore, the final claim at the end of all of this is that therefore the full superpotential of this theory is lambda det M 3n minus nf to the power 1 over n minus nf plus m nf q tilde q. This is the final claim of this argument. Now I'm sure none of you are totally satisfied with this argument. Let's discuss. Questions, comments? What? No. You see, we took some limit in configuration space. In that limit, okay, we could explore all values of this T. Because we had this MNF also in our hands. Okay? So we can do whatever we wanted with this MNF to sort of explore all values of t. This is just some function of an analytic variable. So in some physical limit we could get the form of this function, but for all values of its argument. Okay? Now, sorry?
What if you would have taken the square term?
The square term.
T plus t square.
Yeah. What if we'd taken the square term?
What will go wrong?
Yeah.
Its perturbative with respect to lambda is 0.
Right. Give 1 minute before we address Schumann's question. Notice now that when we take in the limit that all of these a's are becoming large, this determinant of m is also becoming large. There. Now put this determinant of m up here. So this t here was also becoming large. For that reason, we needed to take MNF small, okay, so that we could explore all possible values of t. Since the argument about this 1 plus t did not depend on what the value of MNF was, that doesn't spoil the argument. So this is one reason that we want to take this MNF small, so that we can allow t to be whatever we wanted. Now, Schumann, is this clear? Right? We're going to weak coupling physically, but getting arbitrary values of t, that is very important. Okay, so Schumann, suppose there was a t square term.
If it is arbitrary t,
yes.
Why not you have t square term?
No, because it's arbitrary t, we know we can't have a t square term. Because the theory was weakly coupled, we could arrange for MNF so that the theory was weakly coupled and t was arbitrary. When the theory was arbitrarily weakly coupled, in this limit, a is going to infinity, m is going to 0, no quantum corrections are arranged. So it's only the classical superpotential. So it's because we have arbitrary values of t, that this argument works even for arbitrary values of t. We know therefore that there's no t square term. Is this clear? Of course, the argument was very slippery. And yeah, okay, this is the argument. More discussion. What? The gauge coupling is weak. Why is the gauge coupling weak? Because you see, we stopped the QCD. Let's look at that formula. We stopped this QCD running at scale A, lambda equals this A. This A is taken very large. So this is very small, therefore G is very small. More discussion. What? G, after that there's no further running.
And then how is this form of t 1 plus t?
1 plus t, because you see, the idea is that in such a situation, we get what we would have got before, plus just addition of the mass term. Because you see, classically that's what happens, right? You've got some potential, you add another potential, it's a sum of potentials. Quantum mechanically they can be mixing because you take some vertex from here, some vertex from there, do some loop. But since all quantum effects have shut off, it's just a sum.
And all A's have to be taken to infinity.
All A's have to be taken to infinity for G to be learned, but G to stop running. Okay? But we know we can do it. You see, because as you observed, in order to make this argument, we needed to take m to 0. And when we took m to 0, we saw that we could take all A's to infinity, right? That's what we discussed before. It's not like m is changing the superpotential so much that it's forcing these values to be somewhere. Right? In fact, the thing that will dominate if you let the theory go and evolve to where it wants to evolve, it will evolve to all A's going to infinity. Certainly those were at least approximate vacua of the theory. Okay? It's all self-consistent.
So for small nf that effect doesn't change, that it is.
We'll see in a moment. Certainly at infinity it's doing that, but maybe at some finite value there is a new 0. That we'll see. But first you have to agree to be comfortable with the statement that this is the way. This is the superpotential. Then we can proceed. Yes?
This is just argument or is there any calculation?
I know what you're saying. Most of the calculations are like consistency checks. It's very hard here to calculate. There may be some more serious calculation. You will see how much. See, so the way it goes, in my opinion, is this: that there's some sort of argument, and actually, okay, there's an argument here, but then you check if the whole story hangs together. Okay, and that gives you a lot of your confidence. The whole thing's making sense. Okay, good. So, if you guys are happy with this, we can proceed. Okay, what is the generalization of this to turning on a more general mass matrix? Well, it's pretty clear, right? The generalization of this to turning on a more general mass matrix will be lambda to the power 3 n minus nf by det m to the power 1 over n minus nf plus mij qi qj tilde. Right, if we turn down this mass matrix, it will just be added to the superpotential. And that is the claim, a similar type of argument. Okay, yes? It's because the theory is quantum. The loops are suppressed by the gauge coupling. Okay? And we go to a place in vacuum space, in moduli space, where all quarks, all A's have very large values. Therefore, the gauge group is completely broken down, completely Higgsed. Okay? At some very high scale. Therefore, the gauge coupling stops running at that very high scale. But it stops running at a place where the gauge coupling is very weak from that formula. Okay? In the limit that A goes to infinity, that gauge coupling is 0. So no quantum effects survive. So no quantum corrections to the classical superpotential survive.
But at finite A, you will have some other terms in the superpotential, or this is the full superpotential?
No, claim is this is the full superpotential. You see, because the answer here, the way I wrote it here, didn't talk about A. This is a superpotential which is a function of one complex number. Now we can go to a physical situation where we can determine that function. And once we've determined it, that function is determined. That's the idea.
But somehow you're getting away by determining it in a place where there is no quantum effect.
Yes.
And then you're able to say that even with quantum effects, this is what
Yes.
the answer is.
Exactly. Exactly. That's because you were able to so tightly constrain its form by using symmetries.
Because here we didn't put any constraint on T, that's why, right?
T is some
We can take anything.
T could be anything, that's the point. And in order to be able to take T to be anything, we need to scale M to 0 simultaneously with this in the appropriate way to get whatever T you want.
It's not small t.
It's not small t limit. For all T, we were able to obtain this function by appealing to the fact that we could reach every value of T at arbitrarily weak coupling. Therefore, we know the function. Now, at some other if M was not small and A was not small, was not large, we get the same value of T, but it's the same function. Since there was a place where we could fix the function, that's the function, that's the idea.
It's because this function appeared in that sense.
In this combination. Now, how do we know so tightly that it appears in this combination? Because of holomorphicity. See, if we were allowed to put M stars into this, then we could have put anything. Because M carries some charge, M star can carry, whatever charge we want, we would have been able to get any combination we want. Okay? It's this, the fact that it appears in this combination comes from holomorphicity. You understand that, right? That's like the key place. Okay? You see, how did we get this dependence? This dependence came from the fact that we wanted R prime charge equals 0. This had R prime charge 2, so this had to have R prime charge 2. Okay? That's where, everything came from. Yeah, if we allowed other things, we would be in big trouble. Okay? Excellent.
And if we had N, was it important here for if we had NF less than N for this argument?
For this whole system, it's very important that we have NF less than N. Let me explain why. Determinant of M, this determinant of M on, let's take our, what was M? M was Q tilde Q. Okay? Now, suppose NF is larger than N. Then, M is a matrix. It's an NF times NF matrix. But it's an NF times NF matrix built out of Q tilde Qs, where Q tilde Q contract using color. This tells us that this matrix has at most rank N. You understand, right? Because it's contraction over N values. So the determinant of M vanishes, okay, for NF greater than N. So just writing this down, this thing makes no sense to start with for NF greater than N. Okay, and in fact, basically this is the argument. The same arguments that Affleck, Dine, and Seiberg used will tell you that there is no possible superpotential for NF greater than N. Because the only possible thing that you could have written your superpotential for is not defined. So there is nothing in terms of which you can write a superpotential that preserves all symmetry. Okay? So, though we've worked specifically here for NF less than N, the generalization of this to NF greater than N will be zero superpotential.
Oh, but couldn't you write baryonic terms? We didn't have those because we had NF less than N.
Excellent. We could write baryonic terms, and there will be a place where we will do something like that. Hang on for 2 minutes. Yeah. At least in terms of purely mesonic things, there's nothing you can write down. Yes. But excellent point, we can write something, and you will see. In the case NF is equal to N plus 1, we will and NF is equal N plus 2, we will have superpotentials involving baryons and mesons like this. Hang on for a minute. This will come. Yeah.
How one fixes the powers of lambda and just by dimensional analysis as we fixed for superpotential?
We just, the lambda is not important. But I'm getting it anyway just because I want something dimension 0. Because this is dimension 3, because it appears in a superpotential. This should also be dimension 3, because this already had the right dimension. Right, so we want something dimension 0 and R prime charge 0. Right, so, yeah. Okay, other questions or comments? Okay, excellent. Okay, so we're going to believe, at least provisionally, that this is the actual superpotential of our theory. Let's stick to NF less than N for now. We're going to believe, at least provisionally, that this is the actual superpotential for our theory, and move on. Okay? Some of you guys might come up with further objections to this argument when you think about it. Bring them up next class. Let's discuss it thoroughly. Okay? But right now, let's move on. Okay. So since we probably won't need this table anymore in this class, let me continue on this side. Now, I'm going to check this whole picture for consistency, a little like we did with this Higgsing story. 15 minutes ago. Okay? So, the first thing I'm going to do now is ask the following question. Suppose I have this superpotential. Okay? Suppose I have this superpotential and I now try to look for, I now try to, what I've done is given the nth quark a mass. Okay? So, what I should imagine is that at energies low compared to the nth quark mass, the theory has become SUN theory, but with NF minus 1 flavors of quarks. Because you've made one quark very massive, can be integrated out. Okay? So I want to understand how I can actually integrate this out. So the idea is now I'm going to try to integrate out the nth quark from the superpotential. Okay, so let's look at the equation of motion for the nth quark. Okay, so this, let's call that, I don't know, let's call Q tilde Q equals M NF NF, because it's the NF NF element of the meson matrix. Right? And imagine now that this is a diagonal meson matrix with the other n minus 1 quarks doing whatever they want and this nth quark. Okay? So let's compute the equation of motion that follows from that. Okay. So we get, so I have to vary. So this is lambda to the power 3n minus nf times det m tilde. M tilde is what's left behind when I've removed the, so I'm imagining I've got a situation where I've got this m tilde and m nf nf. Okay? So m tilde, and then there's this m nf nf. And this whole thing to the power 1 over n minus nf plus, there are lots of m nfs, so we have to keep our wits about us. Let me change mass to something else. Let me call it I don't know, Q. Okay, so m nf, the mass. And let me just drop the nf. Let me just call it m, little m. Okay? So it's m times m nf nf. This was a superpotential. Is this clear? Okay? So now we look for some sort of supersymmetric vacuum. Okay? So we try to set del W by del MNF to 0. Okay. So this part is what it is. This is lambda to the power 3 n minus nf by det m tilde. And then we have to the power 1 over n minus nf. And then we have 1 over m nf nf to the power 1 over n minus nf plus m that's what our superpotential is. Now I differentiate with respect to m nf nf. What I was calling Q tilde Q.
Yes. Which you're calling a little nf square.
ANF square. That's correct. Same as ANF square. Correct. So I differentiate with respect to that, and so I get this quantity times 1 over m nf nf to the power now 1 over nf n minus nf f plus 1, and then I get a factor of 1 over minus 1 over n minus nf plus m is equal to 0. Right? Therefore, I get m nf nf is equal to m n minus nf. Now, sorry, n minus nf divided by this business. Let me call this whole thing zeta. Okay, divided by zeta to the power minus n minus nf. Have I got this right, please? So I get m by zeta, that's correct. I get n by nf, that's correct. And then if I raise it to the power minus this, I get this. It looks okay to me. Okay? So, which is equal to zeta divided by m into n minus nf to the power n minus nf. Okay? Great. Now I plug this back in into the superpotential. I've got the value of this m and I plug it back in to see what superpotential I get after integrating out. Okay. So what do we get? We had zeta by this quantity, zeta by m n minus nf to the power n minus nf to the power 1 over n minus nf. Okay, plus zeta, not zeta, plus this quantity into m.
Now you got this zeta as a full
No, zeta was lambda, that quantity.
inside.
Lambda 3 nf, oh, but was it to the power 1?
Inside one or the full?
Yeah, good question. Good question.
Zeta cancels here.
Zeta cancels, sorry. Help me. Sorry. Let's see. So what was zeta? It was including the 1 over m n minus nf. Yeah, you're right.
Zeta cancels.
This with where, let's say zeta equals lambda to the power 3n minus nf over det m tilde to the power 1 over n minus nf. With this you agree is correct?
That is okay, the second line.
This line.
Is full to the power 1 by 1.
Yeah.
Minus nf or the
Yeah. So this is only in the denominator. So you're right. Perfect. So this gives you m into n minus nf. Strange. Okay. Fine. M into n minus nf. That's a bit strange. Usually two things become.
There's a plus one in it.
Sorry, say that again.
Oh, there's a plus one.
There's a plus one. Thank you. Plus one. So, oh God, I messed up badly, right? So, I have to raise to the power
Times and mn, if you can just write times.
times.
The power becomes n minus n plus 1 divided by n.
Yes, I'm just saying whatever the cancellation happens,
Yeah.
write 1 by n.
Yeah, help me, what was the right power? N minus?
N minus n is plus 1 divided by n minus n. I think without the minus sign outside.
Without the minus sign outside.
No, right, without the
Oh God, I'm getting really messed up here. Okay, let's see. Is it without the minus sign outside? Let's see. So I had m is equal to 1 by m. Okay, so this with the minus sign. Then that's yes. Okay, perfect. So then this becomes n minus nf divided by is this now just reversing, right? So n minus nf, just without the minus sign. N minus nf plus 1 divided by n minus nf. This you agree? Yeah, I've just flipped sign. Okay, excellent. Now let me do it again. Okay, so I have zeta divided by this quantity to the power 1 over n minus nf. Oh, it's horrible. Is this really correct?
The way you, the way you written it the last time, I think the plus 1 should be the denominator.
In the denominator? This sounds better. This sounds better. Yes, so we'll write this as nf minus 1. Yeah, that sounds much better. Thank you. Thank you. Okay, thank you, Siddharth. Okay, so then when we write this down, we will get, so now you see what we need to do is to take zeta and then raise this to the power 1 over n minus nf. Right? So this cancels that, so there's a zeta to the power 1 by n minus nf minus 1. And then there is m to the power 1 by n minus nf minus 1. Okay, and then there's the other term, which was, and there was this some number. Okay, and then there was the other term, which was m times this quantity, zeta to the power n minus nf divided by n minus nf minus 1 divided by
Zeta by
m, zeta by m to this power. I'm ignoring these numbers, n minus nf for now. Okay, now do we get the same dependencies in both terms? That's usually the check that this is working.
You are taking the saddle point is
Usually when you do saddle points like this, both terms are comparable. Right. So is this zeta power correct? So let's work out the zeta power. This is zeta to the power 1 minus 1 by n minus nf minus 1, which is equal to zeta to the power n minus nf minus 1 n minus nf. Good. So it's the same. N minus nf divided by n minus nf minus 1. Yeah, same power. M power is probably also the same. That's probably needed by dimensions. Right? So this m power is whatever it is here, and here we get a 1 minus this business, and that's probably also the same, right? Okay, so when I'll leave it to you guys to work it out more carefully. Okay. But in the end, what are we getting? We're getting this, we're getting zeta to the power n minus nf divided by n minus nf minus 1. Okay, and m to the power 1 over n minus nf minus 1. Okay, now we plug in. Okay, so now we plug in, we get zeta was that quantity there, and so we get lambda to the power 3n minus nf by det m tilde lambda to the power 3n minus nf by det m tilde times now the whole thing not to the power n minus nf but to the power n minus nf minus 1. And there are some mass factors. All right, it's this mass factor, just a factor of m. I'm sorry to have been so incompetent with the algebra. Right, because there was that m to the power, that same 1 minus. Is this okay? Okay, excellent. So this is what we get as our final superpotential. This is what we get as our final superpotential for the theory after integrating out the heavy quark. Now we want to compare this with what we expect on physical grounds. Okay? What do we expect? First, we expect that the theory is continues to be SUN, but has NF minus 1 flavors. So it should take the form of the superpotential for the theory with NF minus 1 flavors. Now the determinant behavior is perfect, because it's 1 over det m tilde to the power 1 over n minus nf minus 1. And that's exactly as we expected. Only questions about this number. Okay? Now what should we expect for the number? Well, once again we do matching, right? Once again we do matching. So we use this formula once again. Okay, this formula tells us that this coupling should be constant. So this quantity, when we put lambda here, should be approximately m. When we put the scale equals m, from the lower side and the upper side should be the same, right? Because the coupling constant should be constant. It should be run continuously. And therefore the matching condition is that lambda by m to the power 3n minus nf should equal lambda tilde. This is the what? Okay, fine, yeah. Lambda naught. Lambda naught by m. Lambda tilde naught by m to the power 3n minus nf minus 1. Right, because this is the running coupling formula at scale m for the lower theory, and this is the running coupling formula for this at scale m for the higher theory. Since coupling constant is continuous, these two should be equal. Okay, and therefore we find that lambda naught tilde to the power 3n minus nf minus 1 is equal to lambda naught to the power 3n minus nf times m. So in that formula, in that formula up there, that should have been a lambda naught. So lambda naught to the power 3n minus nf times m is just lambda naught tilde to the power 3n minus nf minus 1. And so what we've recovered is the superpotential that we expected for the low energy theory. Okay, Sunil, so this is one of the reasons, apart from the argument, this is one of the reasons that you believe it. Okay, that you this theory lands on its feet in the sense that it gives you physics and expectation with general physical expectations. Gives you results in concordance with general physical expectations. Okay, so we've seen through this mechanism that turning on masses take us from a theory with same number of colors but one less flavor. Higgsing takes us from to a theory with one less color and one less flavor. Now both of these things can be done repeatedly. You can Higgs repeatedly, you can turn on masses repeatedly, and so basically you can connect any two values of nf and n always with nf being less than n to each other through these tricks. Okay, and so if you're keeping track of the constant behind these things, I was not doing that very carefully. But for instance, in this algebra, we should keep track of all the numbers and so on. If you're keeping track of the constant behind these things, and if you're working in a regulation scheme where these tricks are exact, if one such exists, okay, you can relate the constants in for various values of nf and n to each other. Now, as Diksha is going to tell us, Diksha, with this Thursday work, or do you want a few weeks later for your?
Maybe
Later. Okay. Yeah. So as Diksha is going to tell us when she tells us about the instanton calculation, in the case nf is equal to n minus 1, we can actually calculate the superpotential by another means. Okay, and that the superpotential you get comes with a particular number. So this sort of tells us that the superpotential comes with a non-zero number for all values of n and nf, always restricting to nf less than n, because these are related to each other. One of them was 0, it would lead to contradiction. Okay, finally, now that we sort of understand the structure, we can take this most general superpotential and now compute its compute the saddle point, the vacuum expectation value for m for all n's. Okay, for instance, if you take that mij there to be diagonal and with different values, you get particular answers. You get particular answers for the f term extremization with respect to each of the mesons, each of the m's. okay, or each of the A's that we dealt with. Okay? So what we've done by this mechanism, by taking these masses, is make the theory well defined. You remember earlier it had a potential that went down like that, and the theory had no vacuum. Now we've got masses, and so schematically what happens is that the potential which was earlier going like this, now if you turn on an arbitrary Mij, a full rank Mij, will in each of the variables go sort of like this. Of course, the potential is not affected at very large values of A. The mass doesn't affect the potential at very large values of A. But it changes at small values of A, and enough to always have a vacuum. Okay? So turning on the mass gives the theory a vacuum. Okay? And we could write down, if you like, the explicit expressions for the meson fields. Mij in the vacuum, expectation value of Mij, this is just by varying the superpotential. Mij is equal to determinant of the mass matrix. So now these m's, and let's call this M mass. M mass and multiplied by lambda to the power 3n minus nf to the power 1 over n, okay, times m mass inverse ij. Okay, a little algebra will allow you to do this calculation. So these values of Mij, meson fields, for that mass matrix, we have a supersymmetric vacuum. And these values of Mij, that value of the mass matrix, we have a supersymmetric vacuum. We have a supersymmetric vacuum where all D term and F term equations are obeyed. Okay? So,
this is true for all Ij, individual Ij.
individual Ijs.
So here we always first D to 0 and then minimize the sum of these two potentials.
We put what to 0?
D.
D.
potential.
D to 0 and minimize. Okay, really what you should do is minimize them both simultaneously. Okay? But they don't interfere very much with each other. Because one of them tells you what happens to Q star, and the other one tells you what happens to Q tilde. Okay? The one way of saying it is to check whether you can find a value of A and A tilde that satisfies both this equation and the D term equation. You say the full superpotential is the sum of D squares plus F squares. So we need both to be 0. It's not like they can play with each other. We can't cancel one against the other. Right? So D term superpotential, D term equation gives you some conditions, F term equations gives you some conditions. Okay? Now the D term being 0 gave us the conditions it gave us. These A and A tilde are what they are, up to global symmetries. Okay? Then this is the F term equation. And you can satisfy them both. Okay? So that's the way of thinking of it. What? Yeah, because we had the potential is D squared plus F squared. We will be looking at supersymmetric solutions with 0 vacuum energy. So both D has to be 0. All D's have to be 0 and all F's have to be 0. Clear?
What we have done is we found quantum corrections, possible quantum corrections to the term potential. corrections to the d-term potential.
We could have many corrections to the d-term potential. However, no matter what the corrections to the d-term potentials are, d equals 0 will always solve the d given by this formula. Okay, good. So there are two kinds of things that you could have. See, we had W alpha. Okay. Now, since this is an integral over half of superspace. Okay. Anything that you multiply this must be multiply here must be a chiral multiplet. So you can multiply by more powers of W's, but that will change more than the, it will not affect the potential. There will be some derivative correction kind of thing. Okay. The kind of thing that you might want to multiply by is a function of Q and Q tilde. You might want to multiply by this. Okay. Now, the terms that involve the potential here always involve a d square. This, if you like, I could try to show you. Okay. It's similar in algebraic spirit to the following. Suppose instead of taking phi bar phi as a scalar potential, we had some function of phi bar phi. Okay, so we have some function of phi bar phi. We always get d mu phi ij, and then we get some metric which is a function of phi ij. Now, this term is always 0 as long as these derivatives are 0. Doesn't matter what that metric is. Something sort of similar happens here. Since this question has come up twice, I can try to maybe begin next class by showing you how that works. Okay?
I was asking, can we use this, since this is also integral over the half,
can we try to find, can you try to determine it? I see, now I understand your question. Why not, right? You might think, why not? Yeah. As you know, in the n equals 2 theory, the Seiberg-Witten theory, this is what we're going to do. Right? But I have never seen anyone try to do this directly in n equals 1. Now,
because we have to multiply with the term, with the charge less term, because W alpha d square theta already satisfies the R charge. So one can construct the combination as a combination that you constructed T. Such combination, then F will be a function.
yeah. So what's wrong with that, right? Maybe. What's wrong with that? Okay. Let me think about that. You know, the W's have these, one kind of, okay, I would have to think about it, I don't know. It's a very good question and there's probably a clear answer to it, I don't know. But you're going to have to try to build all possible gauge invariants that you can. Okay? Now, one gauge invariant you will be able to build is Q W Q tilde. So one thing you can do is Q tilde times W alpha W alpha. But another thing you can do is Q W Q tilde. You see, because W is adjoint, it can contract with a fundamental and an anti-fundamental. And I suspect that you see, what was really useful for us, then I would have to think, but I suspect what was really useful for us here was that we didn't have to deal with any color indices at all. The only way of contracting color indices was Q with Q tilde. Okay, W now has its own source of color indices. Okay, so in addition to the obvious thing, that is function of Q tilde times W alpha, there's a possibility of getting Q W Q tilde and Q W Q tilde kind of thing, and maybe that complicates matters. I would have to think. I'll try to find out. I'm sure the right person knows this. Bang on. Yes. What?
What was the question?
The question was, since the power in computing in this game came from holomorphicity, came from the fact that we were dealing with an integral over half of superspace. But Diksha's question, which is an excellent one, is that the kinetic term for the gauge boson was also an integral over half of superspace. So her question was, why can't we compute that? Why can't we say some exact things about that as well? Okay, just like we could for the superpotential, why not for that? It sounds completely reasonable. And in fact, when we study the Seiberg-Witten theory, the n equals 2 theory, since this term, this kinetic term for the gauge boson, it's the kinetic term for the gauge boson that we study, right? That's what we do. But there, as you know, Diksha, there the phi, which is in the adjoint, the superpartner of this, sort of enters the kinetic term in a way that's not just function of phi times function of W squared. The gauge boson, the gauge indices mix. I suspect the same kind of thing will happen here. There, the larger supersymmetry was, I'll find out. But I suspect that the gauge indices are something one needs to keep track of. Okay, excellent question. Other questions or comments? Okay, so there's one last thing I wanted to say before ending. Yes, unique vacuum. Given that matrix, it's a unique vacuum. For instance, we saw that, when we solved for this Q tilde with one M, we got one vacuum. Okay, maybe there may be additional phases. Okay, no, not quite unique vacuum, because there are possibilities of phases. Right, because we had some power. We were solving for some number to some power, and that is equal to something. And then when you invert it, there's a possibility of adding e to the power I those phases. Okay? But apart from those phases, it's unique. And in fact, those phases have an important interpretation. It comes from, thank you, Chintan. Yeah, it comes, okay, in fact, that's what I was going to talk about. Yeah. So apart from this phase business, it's unique.
And these parameters, how are these parameters satisfy the dA equal to 0?
What? Say again?
This M capital M matrix.
So M has to obey this equation, and you have to obey D is 0. So the fact that you have to obey D is 0 tells you that your matrix is up to is diagonal up to similarity transform. So one way to work is as follows: take that mass matrix there and diagonalize it. By a symmetry transform, you can always do that. A UNF times UNF, you can always diagonalize it. Okay. Once you diagonalize it, the form that we wrote down at the beginning of the class that solves the D matrix will also simultaneously solve the F term equations. Okay, so that form then will satisfy both equations. Okay, fine. And if it's not diagonal, then that form, similarity transformed, then that similarity transform is exactly the one that would make the mass matrix diagonal. Will satisfy both. Okay, good. Other questions, comments? Okay, so just one last thing I want to say before we end this class. And that goes as follows. You see, let us now suppose that we've given all the masses, or all the quarks a mass. Okay? Let's suppose that we've given all the quarks a mass, and if we've given all the quarks a mass, well, all of the quarks have values determined by this equation, and then you can plug back. Okay, you can plug back these values back into the superpotential and see what it evaluates to. Okay, and then the superpotential evaluates to something. In fact, by the matching, the matching conditions that we get, it just evaluates to lambda tilde cube, where lambda tilde equals the QCD scale. Okay, obtained after integrating out all the quarks. So let's suppose that, for instance, we take all the quarks and give them some mass, equal mass, and then below that we've got a pure QCD theory. Okay, pure SUN QCD theory, still a non-trivial theory, because the gauge bosons are still running in the theory, even though all the quarks are massive. So we've got a pure SUN QCD theory. Okay, and in the end we get some superpotential that came from this UV theory. But if you work out the algebra like we've been doing in this class, you can rewrite that superpotential, the final value of the superpotential on this vacuum, in terms of the lambda of the effective low energy theory obtained by matching the way we've been doing. Okay, and when you do the calculation up to some number, you just get lambda tilde cube. So W is equal to lambda tilde cube. Okay, you get W is equal to lambda tilde cube up to phases. Phases will come back to. Up to phases you get W is equal to lambda tilde cube, where lambda tilde is the QCD scale below mass m. Okay? Okay, we'll soon have to leave. Okay, fine. Now, what is the interpretation of this fact? You see, below mass m, we've got just some QCD theory. Okay, so our theory, yeah, so we could, for instance, take the mass scale to be very, very large. Okay, so then the fact that we have these quarks didn't matter at all. From that very large scale on, we've got pure QCD and it's coming and running. Okay, now the Lagrangian for pure QCD was W alpha D2. W alpha. And if you naively expand this Lagrangian here, it starts off with integral d4x lambda alpha, because W alpha starts off, for this superpotential, d2 theta, lambda alpha plus blah blah blah. Okay. Oh, what I wanted to say was that the superpotential for QCD, what I should have said was that the thing that plays the role of the superpotential in QCD, the term with d2 theta, is W alpha. Now, what we're saying is that this object here is getting an expectation value. Moreover, it's getting an expectation value that we can compute. Okay, but you see, the term that is it's getting an expectation value with no thetas, right? And so the expectation value you should think of as being generated by this guy. Okay? So our result suggests that pure n equals 1 QCD has a condensate of bilinears of gauginos. Very much like the true vacuum of real QCD has a condensate of bilinears of quarks. Okay? Now the fact that the true vacuum of real QCD has a condensate of bilinear of quarks, okay, is something that the QCD people call chiral symmetry breaking. Okay, the word is used because one of the symmetries, namely the chiral symmetry, is spontaneously broken in this vacuum. Okay, so we inherit that word from QCD people. So the fact that these lambdas get an expectation value is called chiral symmetry breaking. Okay, so one of the things that our results establish, or at least strongly suggest, is that the vacuum of QCD has chiral symmetry breaking, and that the quark condensate in this theory is of order lambda QCD. Is of order lambda QCD. Okay, I'll call him back. Maybe we can end class. Maybe we can end class here. Okay, any questions or comments? How did it come? It came by putting this back into the superpotential. Then you get some expression in terms of the masses, in terms of lambda QCD of the original theory and the masses. And then you ask, but what is the low energy lambda by matching? And just like the calculations we've been doing through this class.
We put NF to 0, right?
What? Yes, in the low energy theory you put NF to 0. Right? So the combination that comes about is precise. In fact, we can do it in a minute if you. Anyway, you guys try it as an exercise. Take m's all diagonal, put all masses equal. It's a simple calculation to do. And check that you get the lambda. The thing that you get is in fact lambda cube, where lambda is lambda of the low energy theory. Okay, maybe we. Yeah. Okay, in the next class we will continue our discussion of the n equals 1 theory, but now moving away from nf is equal to is less than n. We'll come to these baryonic superpotentials that Siddharth was talking about.